Okay, so we're going to look at how to do a two-way analysis of variance, do the checks on the assumptions of the analysis of variance, which is checking for equality of variance using Levene's test, and checking the residuals for normality, and then doing the post hoc test afterwards. So we've got a data set here then where our response variable, which will be on the y-axis, is the percentage moisture content of a cereal grain. And the two treatments are how long the cereals were in the oven. So we've got in a drying oven. So we've got 30 minutes, we've got 60 minutes, and whoops-a-daisy, we've got 90 minutes there. And we've got three different oven temperatures. So 135 degrees, 125, and 130 degrees. So this is a two-factor analysis. We're looking for, is there a significant difference in the amount of time in the oven that's causing a significant difference in the percentage moisture content of the grain. We're then looking to see if there's a significant difference of the percentage moisture of the grains at the different oven temperatures, and we can also see if there's a significant interaction. Is there a significant difference in the mean moisture content of the grains across the different oven temperatures, and is that different with different oven times? Okay, so the first thing we want to do in this analysis is have an eyeball of the data. Let's make an interval plot, and we'll do a with groups interval plot where the response variable is the percentage moisture of the grain. The two categorical variables are of course oven time and oven temperature, but it's useful to add some colour to the graph. So by putting in here the categorical variables that I want to have different colours for, I'll use oven temperature. So I can either choose oven time or oven temperature there, but I've just chosen oven temperature. I click OK, OK again, and eyeballing my data, look, yes, there's some quite significant no man's land in between some of these confidence intervals here. When we've got no overlap of confidence intervals, that's a really good indication of a significant difference. But then what's going on up here? Clearly, the percentage moisture content of the grains is lower the longer it was in the oven at the higher oven temperatures. But we want to start pulling out some significant differences here. We want to know, is there a significant factor of oven time? Is there a significant factor of oven temperature? And is there a significant interaction? So we're going to use the two-way analysis of variance to do this. But before we do any analysis of variance, we've always got to check for equal variances. See all these different magnitudes of space, different magnitudes of sizes of these error bars. We want to know that basically the within factor error needs to be not significantly different. If I had one error bar, for example, that was absolutely huge, it was straddling right across here, then that's very likely to be a significant difference in the variances. And then I'm not going to be able to look for the between factor variances, which is sort of what the ANOVA is doing. So I've got to check for equal variances first. This is crucial when I'm doing any analysis of variance, or in fact now in Minitab we do it all through this option, don't we? The fit general linear model, which is much more useful for us. So test for equal variances. I put in the percentage moisture content of the grain, my response, my y variable goes in here, and I've got then the two factors, oven time and oven temperature. It doesn't make a difference which order we go in, just put them in, click OK, and all this stuff's interesting, but I just want to go straight down here and look at this Levene's p-value. I can say there is no evidence of non-equal variance because my p-value from the Levene's test is above 0.05. So in a experimental project write-up, I could just say at the start of my results section that the data was checked for non-equal variances, comma, no significant difference between the variances was found, and all I would need to write is Levene's test test statistic equals 0.60, p equals 0.770. That's it. That's all we need to write. We don't need to show anything else, but it's crucial when we've used an analysis of variance or a general linear model to analyze our data, that was crucial that we show that we've checked for equal variances. I'll do another video after this one which will tell you what to do if that p-value there comes out to be less than 0.05. It does that an awful lot of the time when we've got real data. But there's some ways around it which I'll talk you through in the next video. So we want to do the analysis. I go to do the general linear model. I want to fit the general linear model. My response then is the percentage moisture content of the grain. My two categorical factors go in here, oven time, oven temperature. Doesn't make a difference which way round I do that. I then need to go into click this model here, and because I want to see if there's a significant difference in the moisture content of the grain across the 3 levels of the oven time factor and across the 3 levels of the oven temperature factor, but remember I also want to look at the interaction. I want to see, is the effect of oven time the same across the 3 oven temperatures? So when we do this 2-factor analysis, it's very often really interesting to put this third interaction factor in as well. It's a really useful thing about the sort of 2-factor experimental design. Lots of experimental projects seem to have this experimental design. It's a good one. I want to store the residuals, remember, which is how much each observation differs from its group mean. So how much, for example, this observation here in the first row, it is then at the oven time of 30 at 125. So we can see we've got 1, 2, 3, 4 observations at that particular 2-factor level. There is then going to be the mean moisture content for these 4. The residual is how much this observation here differs from its group mean, then how much that factor differs from its group mean. By storing those residuals, they're going to appear in this next column C4 along here. It's those residuals that I need to check for normality at the end. Although there's some caveats there, which I'll explain at the end. There's no point ever checking the actual raw variable itself in C1, the response variable. I don't ever need to check that for normality. We need normal distribution of the error terms or the residuals. They need to be normally distributed when the sample size is small. As the help menu in Minitab will explain to you, when the sample size in a regression or in an ANOVA starts to get really large, then non-normal residuals become less of a concern. Non-equal variances is always got to be present. We've got to have that. That's sort of non-negotiable. If you haven't got equal variances, the ANOVA general linear model analysis stops right there until you can correct those non-equal variances. So I've clicked OK, and here's my analysis. So we've got 3 factors here in this analysis of variance table. These 3 factors have then had their own F value computed against them and their own P value. So we've got a null hypothesis for each of these factors. So this first top factor here, the null hypothesis, is that there is no significant difference in the percentage moisture content of the grains purely across the factor of oven time. And that null hypothesis, look, we reject. The p-value, remember, it's never 0. The p-value is just not resolved at 3 decimal places. If I right-click here, I could then increase the number of decimal places, and we can see, look, it's not 0. It's just very, very, very small. It's far too small. It's so far below our level of significance, we can just report that as p is less than 0.001. That's a highly significant effect of oven time on the percentage moisture content of the grain. So that null hypothesis is rejected. Then for oven temperature, we can see that we've rejected the null hypothesis that there's no significant difference in the percentage moisture content of the grain across the factor of oven temperature. The final one then is the interesting one. And look at that p-value. Really, it's just a whisker above 0.05. Really, if we resolve that to 2 decimal places, we'd really want to be rejecting that null hypothesis. We've got a weakly significant interaction. So that's telling us that there is the effect of oven time on the percentage moisture content of the grains is not equal for all oven temperatures. Okay, so then I can scroll down a bit further, and we've got good old R squared down here. Look, 83.09% of the variability in the percentage moisture content of the grain is explained by these two factors and their interaction here, by variability in these two factors and their interaction. So that's leaving me 16%, just above 16% of the variability in moisture content that's not explained by oven time variability, oven temperature variability, and the interaction between oven time and temperature. So we've clearly got something going on that's worth reporting. We've got some significance here, and we can start to, we don't know, well, we saw from the interval plot earlier, and it's fairly obvious what the effect is, but we don't know if there's a significant difference between, say, 30 minutes and 60 minutes or 90 minutes. So we want to start doing our post hoc testing to see which factor is different from which. Where does this significant difference lie in the raw data? Before we do that post hoc testing, there's the residuals there stored, so we can see how each observation differs from its group mean there. So I'm just going to do a very quick graphical summary of those residuals just to check we are not too non-normally distributed. And look, there's my Anderson-Darling p-value. We can see the bell curve there. There's a bit of a positive skew going on there that we can see in this skewness value, but really the null hypothesis that the distribution of those residuals is not significantly different from the normal, I'm failing to reject that null hypothesis. So we've got no obvious violation to the assumption of the analysis of variance. So I want to go and do my post hoc testing. Go to general linear modeling. See, all these options have come up now. Look, I could do comparisons, which I'm going to do in a minute, but then we can do factorial plots and predictions and all that should we want to. But we want to do our post hoc comparisons. So I'm going to do pairwise comparisons using the Tukey method, oven time, oven temperature, and the interaction. We will keep our confidence level at 95. Graphs, no, we don't want those. Results, I think we'll just keep the grouping information. Remember, we could also get Minitab to give us p-values against all possible pairwise combinations. So the mean moisture content at an oven time of 30 minutes at 125 degrees C, is that significantly different to the mean moisture content at 30 minutes at 130 degrees C? All possible pairwise combinations across those two factors, we could get a p-value which would go against the null hypothesis that those two means are not significantly different. I'm not going to bother with that. We're going to stick with the good old A, B, C Tukey method, where means that do not share a letter are not significantly different. So I'll just click there, click OK. There's my A's and B's purely for the factor of oven temperature. So what we can see here, look, is, remember, we've got a significant effect of oven temperature that was reported by the ANOVA earlier on, that we've got a significant effect of oven time, significant effect of oven temperature, and the weakest of significant interactions. It's weak, but it's not something I'd want to go ignoring. So there's my comparisons. Notice how in Minitab 19 we can navigate between all the things all the analyses we've been doing. We can go work our way right through everything we've done much easier than we could in Minitab 18. Big improvement there. So I can see that there's no significant difference in the moisture content, the mean moisture content between 130 and 135 degrees C, but the mean moisture content is higher, significantly higher at 125 degrees C. So far, so interesting. The oven, that was oven time, that oven temperature down here. We can see then the oven time of 90 minutes gives a significantly lower mean moisture content compared to 30 or 60 minutes. What we're really interested in, though, is these interaction terms down here. Look, so we've got all of these groupings here by, if we share a letter, means that do not share a letter are significantly different. So once we've got to 60 minutes at 135 degrees C, the mean moisture content becomes significantly lower than 30 minutes at 125 degrees C. Because all these share the letter A and B, they're not significantly different. So these B's here are significantly different to that single A on its own. It's once we get to 90 minutes at 130 and 90 minutes at 135 degrees C that we get a significantly lower moisture content. Those A's, B's and C's, I could then annotate those onto my interval plot. So I could start editing my, I could start editing my interval plot here. So I think, right, well, I want to put on my C's. I know those belong down here, so I'm going to put a nice capital C there, and we'll have another one down here. So you can see how it's easy to just start annotating those onto your graph. The graph needs an awful lot of work though, doesn't it? As we look at this graph, it's definitely not ready to go into a report yet. I mean, that title needs some editing. Down here I've got oven temperature on my x-axis, but it's also up in the legend showing me how I've coloured my intervals by temperature. So I don't need it down on the y-axis, so I can come on the x-axis, I beg your pardon, so I can come and edit that down here. Show, I don't need to see oven temperature. Labels, I don't want the oven temperature label on the x-axis there, so you can go 2. So yeah, that's a little bit better now. Now maybe I might be thinking, I might want to put on, for example, let's see if we can add a mean connect line. Because we've got these oven times, we might be then thinking we want to see, we just want to connect those means up. So we can see, this is starting to hint to us this interaction effect. Imagine if all those mean connect lines were all totally parallel. That would show us no interaction at all. Though there is no interaction, that would tell us that the effect of oven time on the percentage moisture content of the grain is the same across all oven temperatures. That's not the case because those mean connect lines, look, are not parallel. We might also be thinking, well, on my graph, I don't want to show confidence intervals of the mean. I'd rather be reporting standard error, so I can edit my interval bars as well. Right click on the interval bars, go to options, and instead of choosing the 95% confidence intervals, we can get the standard errors. Now we need to be careful here because that's obviously made my graph look much, much more interesting. With the standard errors, look how the error bars have shrunk. So it can be tempting to plot that graph because it looks more impressive than the previous one where there's much more overlap. But we've got to be careful with what we're inferring from the graph, because when I'm reporting standard errors of the mean, I'm only reporting the error that's inherent in the sample that I've got. If I show confidence intervals of the mean, then I'm sort of extrapolating out to the wider population. I can't look at these errors here and go, well, because there's no overlap of the standard errors, those two must be significantly different. We know that those two are not significantly different. So it's always, we've got to be very careful what error bars we show. If you're then using a graph and you're then wanting that graph to show you which group is significantly different from what, then you're much better off sticking with your confidence intervals of the mean. If you're happy that you're just wanting to report, just using descriptive statistics to report the data, the error inherent in your sample, then stick with the standard error.